Okay, so let's start from a recap of last lecture. So what we did is that we obtained the full replica symmetric breaking equations that I will write right now. So we obtained a flow equation for a function f. So let me write it like this: the x of f this index x runs from 0 to 1, and this function q of x is from 0 to 1. So a generic form will be something like that. Okay. And this equation is very general. It comes from the part of the free energy that is given by e to the 1/2 a b from 1 to n. Okay, so this is quite generic. So whenever you have an operator that is of this kind and you do a hierarchical ansatz for this matrix Q, you get this equation. Okay, and then the boundary condition for this equation is simple. So you have a boundary condition at x equal to 1. So here. And this is just the log of gamma 1 minus q1. So here I'm supposing that we are in the SAT phase. Okay. Otherwise, you have to replace this function by e to the minus beta VOH. Okay. Okay. So we showed that in order to compute the free energy with an ansatz of q of x of this kind, what we need to do is to enforce this equation. And in order to do that, we introduced some Lagrange multipliers that are two functions. Let me write them here. So we had P1 and H, that is the Lagrange multiplier that you need to enforce the initial, the boundary condition for the equation for f. And then we had another Lagrange multiplier that is needed to enforce the initial, the flow equation for f. Okay. And at the saddle point level, we have an equation, a flow equation for this function, that is the following. And we had an initial condition, a boundary condition. Now at x equal to 0, this is just a Gaussian computed at h plus sigma. Okay? And then given these two sets of equations, we had a closing equation that is, okay, I can write it, let me write it here. That is Q0 over 1 minus Q squared Okay. So given this set, so these sets of equations just give you the saddle point equations from which you can obtain the profile of Q of x. Okay, that is what we want to obtain. And then we show that starting from these equations, we have two additional equations that I will write here. So we have a first equation that contains the idea that the solution is marginally stable. That is 1 over lambda squared equal to, sorry, here there is okay, so this holds whenever Q dot of x is greater than 0. Okay, and in the same region we have another equation that tells us that x is equal to lambda of x over 2. And then here we have, let me write it this way. Where this average is just the integral over p of x and h. Okay? Yes?
Can you remind us of lambda, of the meaning of lambda?
Lambda? The expression. So lambda is 1 minus x q of x minus, wait, it's, wait, before I say something wrong. Yes. Okay. Okay. So these are the saddle point equations. And now the program for today is to obtain the properties of the jamming transition when it is in the full RSB phase. So let me just remind the phase diagram. So here we have sigma, and this is alpha. So we have a replica symmetric jamming line here, and here there is a full replica symmetry breaking jamming line, and this is where replica symmetry breaks. So this is the dot line. So here the solution is RS, and here it's RSB, and in particular close to the jamming line, it's full RSB. So you have a part of Q of x where this condition is satisfied. Okay, so close to the jamming line here, it's full RSB. Okay, so the idea is that we would like to understand the properties of the solution of these equations close to this line. Okay, we already analyzed the properties of the saddle point equation close to this line. So here the solution is always replica symmetric, and this is the convex and what we would like to do is to repeat the same analysis, but in this case.
Sorry, Francesco.
Yes.
Can you explain last time you said that in different regions of the phase diagram you have RSP and full RSP.
Yes. Okay.
How can you tell that? I mean, how can you tell when the full RSP solution starts?
Okay. So
I mean, did we already see it or
no? I mean, I didn't tell you how to extract the properties of the full RSP solution from this equation. So if you want, I can tell you briefly. Okay. So what I discussed last time is that from this equation, you can obtain this line, right?
Yes.
Because this equation, if you compute it on a replica symmetric solution, it becomes exact. It holds only at the replica symmetry breaking transition point. Okay. So this equation gives you this line.
Okay, and that equation is for the full RSP solution, right?
Yes.
Okay.
But I mean, here this equation just tells you that if you have a point where this condition is satisfied, then this equation holds.
Yeah. Oh, yeah. Okay.
Now it turns out that here this phase diagram is a bit more complicated in the sense that at some point there is here a dynamical line, here there is a static line, and here there is a Gardner line. Okay, so what are the properties of these these lines? So here, so in this region, when you cross this line, what you have is that here you have really a full RSB solution. So here it's really full RSB. Okay. Instead, what happens here is that here the solution is first of the 1 RSB type. So the Q of x is something like that. Okay. And then when you arrive, and when you cross this line, so if you increase alpha, so if you increase the number of constraints, when you cross this line, it turns out that this part develops a kind of continuous path here before reaching the jamming transition point. Okay. So this gives you this part of the line. And when you arrive here, so you have two additional lines, because what happens below this point that we call sigma 1 sigma RFT. So what happens below this point is that if you are in this region and you look at the space of solutions, so the space of solutions is clustered, but here the partition function is given by clusters with finite complexity. So if you plot, so here when you cross this line, the space of solution goes from something that is ergodic, you have just a single ergodic component, to something that is clustered. But now if you compute the complexity, so how many clusters you have, in this region the complexity is positive. Okay, so you have, so if you call small s the internal entropy of these clusters, so how many solutions you have inside one cluster, okay, this is the log of this number is small s, then you can compute the complexity, that is something like that. Okay, so you will have, in this region you will have a set of clusters, okay, that you can organize according to their complexity. Okay. And it turns out that in this region, when you increase alpha, here the Boltzmann measure, that is just a flat measure over the solution, here is dominated by clusters that have the maximal complexity. And then when you increase alpha, this goes down. So the dominant clusters have less and less complexity. up to this point, where actually the complexity of the relevant clusters is 0. Okay, so this is called a dynamical transition line. And it's exactly the same that you have, for example, in glasses, or in the constraint satisfaction problem that I was discussing in the first lecture. And this line is a static transition line, or Kauzmann transition line, or Kauzmann, or condensation in the context of constraint satisfaction problem. So when you cross this line, you have, of course, you have a 1 RSB solution. Okay. And now when you increase alpha, at some point you cross this line, and this plateau actually breaks again, and it develops a continuous part. And so when you reach the jamming transition, you always have a kind of continuous part in the Q of X. Is it clear?
Yes.
So this is the description. So how you can obtain this from this equation is a bit complicated, but yes.
So I would like to ask if in the second part of the diagram, where you go from RS to static 1 RSB
Yes.
before going to full RSB. So
Yeah.
on the
Yes, here.
yes, on that line. So the replicon is 0 or not?
Yes, it's 0. Why not?
No, so because we are going from RS to 1 RSB there.
Yeah, but it's a static transition. It's continuous. So what happens here is that, so you have a solution that for Q of X, let me write it here, that is flat, and it's opening continuously. So when you cross this line, so you have something that does like this. And then when you increase alpha, the distance between these two plateaus increases. Okay, so it opens continuously. Okay. Okay. Thanks. You had a question?
Yes, but now yes. The complexity, the sigma,
Yes.
is a mean measure. I mean, it's a measure on all the clusters. It's mean complexity of.
So
All the clusters. I mean, is the number of solution in average in the clusters?
no, okay. So let me discuss it
Or-
a little bit in more detail. So when you cross this line, you have the space of solution that gets clustered. So you call S, small s,
Yeah.
the internal entropy.
Yes, but
So-
I mean, of which cluster?
Each cluster has its own internal entropy.
Okay.
And now you can make an histogram
Uh-huh.
of clusters that have exactly the same internal
Okay.
entropy in the thermodynamic limit.
Okay.
So this is an intensive quantity. So it's not the extensive internal entropy, it's the internal entropy divided by n.
Yes.
Okay. So you will have
Okay.
clusters with different internal entropies.
Okay.
And here you plot the log of their numbers.
Mhm.
So this is the log of the number of clusters that have internal entropy
Okay.
as mean. And this is the log of the number of clusters that have internal entropy as mass.
Mhm. Okay, but it's not the complexity itself that changes when you cross the.
The complexity changes. So it's not a function that is fixed. When you increase alpha,
Yes.
this curve changes. But for each alpha, the dominant clusters
They also change.
they also change.
Okay.
So
and that's
here,
what is important for the
so
for defining the transition line.
yes.
Okay.
So when you cross this point, you have this curve,
Mm-hmm.
and here the Boltzmann measure is dominated by the states. Then this curve evolves.
Okay. Yes. No, it's.
But
it's clear.
when you arrive to this point, the dominant clusters are these ones.
Okay.
Okay.
Thank you. Yes. Yes.
Okay. How to derive this from these equations is a bit involved, in the sense that you have you should compute an additional equation, and the way in which you compute it is always the same. So you take this equation you derive with respect to x. So if you remember, in order to obtain this equation, we took this equation and we derived with respect to x. We got this. Then in order to get this, we took this equation and we derived with respect to x. And if you do the same, starting from this, you get an equation for q dot. Okay. And now, if you take these equations, so this will be something. Okay. If you take these equations and you compute them on a replica symmetric ansatz, which means that you are here, and you are looking at these equations on this line, so what happens here at this point is that this thing becomes negative. And it cannot be negative, because you cannot have a q of x that has a negative part, because these flow equations are not defined when q of x, the slope of q of x is negative. So when this becomes negative, you get this point. Okay. And when you reach this point, so the point where this q of x breaks goes to 1. And in principle here it's greater than 1, but this is not possible because the q of x is a function defined between 0 and 1. So here there is something that shows up. So that's how you get this phase diagram. Okay. So this line of reasoning was, I think that was introduced by Sommers. There are a series of papers of Sommers where he does everything in the Sherrington-Kirkpatrick model, and we did it in the percent. Okay. But this is a kind of recipe to get the phase diagram. Okay. So now the plan is to look at how these equations behave when you cross this, when you reach this line from below. So we want to approach the jamming transition from the start phase. Okay.
Francesco, how do we know that the sat ansat transition is still here? Because we computed it for replica symmetric, right?
Mm-hmm.
And we know that it's RSV. So is it still at the same point?
No, it changes. So in principle, you need to compute the full RSB solution in order to see what it is. Okay. Now we assume that it's there, and we try to compute the properties on that line. Okay. So before, okay, I always erase the wrong thing. Okay, so the first thing, so what we would like to study is the critical properties of jamming for in the non-convex phase, so for sigma. So the first thing that I would like to do is to switch from q of x to x of q. Okay. So I just rewrite everything. Instead of using q of x, I will use x of q. And so the flow equations will be, so here I have a derivative with respect to q. And this is the f of q and h. Okay? And this is equal to minus 1/2 and the same initial condition. So let me assume that q of x is something like that. Huh? So this is q small m. This is q big M. Okay. That's it. And therefore f of qm is just the log 1 minus qm Okay. Then there is the other equation for P. It's exactly the same. So this is x of Q. And of course you have the other two equations. So you have 1 over lambda so this average is done with P of Q and H.
Sorry, prime is still the
Derivative is back
of
to
P.
H. To H.
To H, sorry.
So this is okay. Now so when we did the replica symmetric solution, the jamming transition at the jamming transition we had that Q was going to 1, right? Because we had that the space of solution was shrinking to just a point. Okay, so when you reach this line, the space of solution shrinks, and therefore Q goes to 1, right? Now here we are in a situation that is a bit different because we have a Q of X. And so how does the jamming line, how can we define the jamming transition line? So remember that when we had the Fourier SB solution, we said that the solutions, when you have a Fourier SB part of the phase diagram, are organized into clusters of clusters of clusters and so on. So you have a big cluster of sides Q0, then you have clusters of sides Q1, and then this hierarchical tree or kinetic tree. Hence, so this goes on up to the point where you have actually clusters of solutions. Okay. With our sides Qn. Is it clear? Okay. So here all these levels are clusters. Okay. Only the last level are clusters of solutions. So here you have clusters of clusters, and when you arrive to this point, you have clusters of solutions. Okay. So when you reach the jamming line, what happens is that these clusters just shrink to a point, and therefore Qm goes to 1. Okay? So what we would like to understand is what happens to these equations when Qm big M goes to 1. Yes?
Could you explain again how it makes the link between Qm and the size of the cluster?
So, what is Q? So remember that QAB is 1 over M. Okay. So if I take A and B that are inside the innermost clusters, then this just gives me the distance between two typical solutions that are in the innermost cluster, and that belong to the innermost cluster. So when you increase the number of constraints, this cluster just shrink continuously to 0, and therefore these two solutions just coincide because you have just one solution, and then everything disappears. Okay, so here, is it clear? That, okay, so this is the Jamming limit. And we would like to see what happens to these equations when we take this limit. So the plan will be the following. So first I will describe the scaling solution. So these equations admit a scaling solution. Then I will introduce and discuss the critical exponents. And then I will compute them. Okay. And finally, I would like to discuss this in the context of vacuums of our spheres. Okay. Okay, so let me introduce epsilon as the distance from them. So if you take the phase diagram, so we take, for example, you can fix sigma, and then epsilon is just alpha minus the jamming point. Okay. Otherwise, you can fix alpha and go in this direction and have epsilon is sigma minus sigma j. So it's not. So it's just the relative distance from the jamming point. And now what we do is that we introduce some scaling variables. So we have epsilon of q. And then we introduce f hat. So this is epsilon f. And then we have lambda hat. Okay. And then we assume that qm is 1 minus epsilon to some critical exponent k that we will compute. Okay. So when epsilon goes to 0, qm goes to 1. Okay, let me just tell you what is the interpretation of this exponent. So let us go back to our spheres. So our spheres. So we discussed that a way to describe the evolution of an sphere system is to compute the mean-square displacement as a function of time. This is so this is the relative distance in phase space from of the system at time t from its configuration at time 0. Okay. And if you are in the glass phase, we discussed that this thing is something like that. So this part is a ballistic part. So delta increases in a ballistic way, and then it saturates to a plateau. Okay. We call this plateau delta E, but actually we could call also delta M. Okay. So what is this plateau? So when you are at, so this is at finite pressure, right? So when you have the spheres, so the spheres are inside an amorphous structure, and they just vibrate inside the cages. Okay, so the height of this plateau just gives you the amplitude, roughly, of the vibrations of the spheres inside their cages. Okay, so when you compress the system, of course, this amplitude shrinks. Okay, because you are compactifying the system. And so when you increase the pressure, this function evolves in this way. And then when you reach the jamming point, this thing goes to 0. Okay? So this is when the pressure increases. And actually, if you do numerical simulations, you realize that this plateau goes to 0 as the pressure to minus k. Okay. And this k has exactly the same meaning as this k, right? Because this function, okay, so the amplitude of the vibrations is exactly this thing. So it has exactly the same meaning, right? Is it clear? Okay. So in principle, these two exponents are different, but we will see that they are the same. So our spheres and the perceptron are in a kind of, let's say, in the same universality class. Okay. Okay.
Sorry, but you have to go to infinite pressure.
Yes. Yes.
For instance, when you have this transformation, introduce y, f hat and stuff, so somehow you assume that x is, you know, x would be small, and so because of that you divide by small parameter epsilon,
No.
and y would be no?
No, actually x stays finite. So, okay, let me,
Sure.
so if you take this, then epsilon of q, so it's so let's say, okay, so okay, and q is inside this integral. Actually goes in qm, small m, and 1. Because qm is going to 1, right? So the scaling solution appears when q goes to 1, so in the regime where q is close to 1. And actually epsilon goes to infinity. Okay? So x is really fine.
Epsilon is actually large, yes.
Yes.
But why you use this notation epsilon? Everybody by default believe epsilon is something small.
Yes, it's something, yeah. But, I mean, this is, I mean, sorry. No, I mean, the point is that, okay.
Fine.
Okay? Okay, let's see. Okay. So when you have this, then, okay, let's see, just describe the scaling solution. So so epsilon of q goes like 1 minus q minus 1 over k. And then we have, so when q goes to 1, and then we have p of q, that when q goes to 1 becomes of this kind. So everything that I will write holds when q goes to 1. So it's 1 minus q minus k over k minus h. So you have three regimes. This is for negative h. So then you have 1 minus q minus a over k and then you have a regime where for positive h, this is a regular function when q goes to 1. Okay, so this is a scaling ansatz for p of q, and this depends on another critical exponent. The critical exponent is a. Okay, so this is another critical exponent. So the fact that you have these three regimes, I will show you that there is a way in which we can obtain the fact that you have two regimes here, and then once you have these two, you should have a matching regime here, and this one will be the crucial one. And finally, so this is the scaling form for P. And now I would like to describe the scaling form for F. So let me introduce M of Q and H. And this is prime. And this I will say that when Q goes to 1 is minus square root of 1 minus q, and then we have a scaling function of course when q is 1. Okay.
And that last walk for h or for the square root of 1 minus q?
Yes, so when you are at the borders, and I will show you. So m, so let me call this scaling variable t. So m of t, so t to infinity is 0, and m of t minus going to minus infinity is t. Okay. So these two limits you can already get when q is over big M, q big M, because when this is just the boundary condition for the flow equation of F. And I will show you that this is also true when q goes to 1. Okay. Okay. So let me start from exactly this. So let's take back f of q and h. So the initial, the boundary condition, the initial condition is that q big M. That is the log 1 minus gamma of 1 minus qm. Oh, really with the theta, the initial theta. And this is for h that goes to minus infinity and infinity is 0 if h goes to infinity, and this minus h squared divided by 2. You can just work out the asymptotic expansion of this is simple. Okay. And now let me consider the flow equation for f of q and h. And now what I would like to do is to see that when I take these two limits, I want to show that this function I would like to show that this, when you plot this into this equation, you get that this satisfies this equation. Okay. So this is coherent with the initial condition, the boundary condition. Yes?
Sorry, I do not understand the condition. The first h to infinity, the second h to
minus infinity.
minus.
Sorry. Okay. So this is consistent with the boundary condition. And I would like to show that this is a good solution when h goes to infinity and minus infinity. It's a good solution of this equation. Okay. So what we can do is just plug this inside this equation and see that it's good. Yes?
So the scale you introduce for p, for example, is it something you get from the equation? Something you...
Yeah, I will show you how we can get this scale. Okay. So I will show that there are two regimes, and then you need a matching regime, because these two are very different, right? This is something that doesn't scale with q. It's a regular function when it goes to 1. Instead, this is you have a scaling function, so there should be a matching regime. Okay. So for this thing, there is nothing to say. This is, of course, satisfied. If you plug 0, there is nothing to say. And the second one, it's easy. So if you do, so we have f dot. This is so let me just remind that lambda q is 1 minus qn q. So it's just the lambda of x, but using x of q instead of q of x. Okay, so it's just a simple change of variable, change of variables. So this is when you take the derivative with respect to q. Maybe there is a plus. Sorry. Yes, sorry. So this is minus. Okay, so this is the left-hand side. And let me compute the right-hand side. So when I plug this into this expression, so what do I get? So I get just -1. So this is -1 over lambda plus h squared divided by lambda squared. So for h that goes to -infinity, this doesn't matter. So this expression is dominated by this one. And therefore you get the same. Okay. So this is a solution of this equation when h goes to -infinity. Okay? Okay. 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 So now let me consider the equation for m. So I introduce m of q in
But-
h.
For instance, I even forgot what is f, but if you somehow, you just write and you check and it works. Yeah, but how you do it? For instance, if you know maybe intuition which are in advance, then for h going to -infinity, f becoming very large, so you drop f to prime factor, and the equation simplifies. Maybe you can almost derive that solution
Yeah.
from there.
Yeah.
And that's how you did it.
No. The way which we did it is first we solved numerically the full RSB equations, and then we understood how they were behaving, and then we wrote the scaling form, and we checked that it was consistent. So the intuition is, there was no intuition at the beginning. There was, so we knew that some scaling solution was coming out. So we computed the solution numerically of the equations. And then starting from the solution at finite pressure, or at finite epsilon, we kind of try to get some answers for the...
Yeah, but for instance, if you drop f to prime,
Yes,
your
yes.
equation becomes first order, so it's
Yes.
hyperbolic. And so in principle, of course, not quasi-linear, but in principle, method characteristic can give you a solution. So maybe you can discard.
Yeah, and that one is just asymptotic.
Yeah, but for large.
Okay, so let me get back this. So this. So you can, using this form and using the flow equation for f, you can obtain the flow equation for m. So I will not do it, but it's very easy. This is just and now let me consider this object. Okay. So let me compute lambda. So when q goes to 1, we have that, we say that epsilon of q 1 minus q over q. And now let me compute the asymptotics of this when q goes to 1. So this is 1 over epsilon lambda of q is 1 over epsilon. Okay. So what is this? So this is equal. So this thing is epsilon to the k. Right? So this is epsilon to the k minus 1. And here I have plus qm. Okay, let's try this way. Okay, and now we use this. Okay, so this is okay. So we do all the algebra, and what you get is. Let me write just the final expression, but it's just simple. So let me say this is, let me put up the factor here. Okay, so here I have, okay, so this is 1 minus okay. And now let me consider again this. So this is just and then we have this expression. So okay, can I do one thing? It's faster. So this is okay. Now if I say that 1 minus x is bigger than epsilon to the k, then this term is bigger than this one, and therefore this is okay. So now what I do is that I take this and plug it here. Okay. And then we take a break. So then we say that m and the root is so we have that m dot. So let me call this variable t. This can be variable t. So m dot is just 1/2 minus t m prime. But here the derivative is with respect to t. And then you can compute the other terms. Okay. And these are so So when you plug this into these equations and you use that this is given by this term, then you have a scaling equation for m. Okay. And the scaling equation for m is 5. No, sorry. It's m of t minus t and prime. And using the asymptotic expression for t going to minus infinity plus infinity, because of course t is proportional to h, so you have m of t going to infinity is equal to 0. Is equal to t. So if you fix k, then you have a unique solution for this equation that has these two asymptotic behaviors. Okay. So fixing k, you get an m of t.
First limit again, t going to minus infinity, or here minus. Second.
Yes. Okay. So this is the first piece, and then I think that we can make a break, and I discuss the equation for t. Okay. Wait.
Right.
Okay. Don't. Sorry. Now we start with the. So we analyzed the equation for f, the scaling form of f. Now let's take back the equation for t. So we have. So now the dot denotes the derivative with respect to q. So now. Now, so if h goes to plus infinity, we have that f goes to 0, right? So this was the large h behavior of f. And therefore you have that p q with h is just to this is for h going to plus infinity. This happened. Okay. And therefore the solution consistent with this boundary condition will be it's just the Gaussian plus h plus sigma. Okay. Now let me study what happens for h that goes to minus infinity. So here we have that f prime. It's known as h over lambda q. So remember that in this case we had f of q and h equals minus h squared divided by 2 lambda q. Okay. So you can plug this into this equation. Okay. So what you get is this equation. So, okay. E dot is equal to 1/2 p second plus 2 x of q. P prime and h plus p. Okay. And now what you can do is that you can try a solution of this problem. That is, so here you have a function d. There is a function of q. And if you plug this into this equation, you just get an equation for b. And the equation for b is so here you see that you have again this combination that appears, and you know that this is connected to minus 1 divided. Okay, so here you naturally get minus 1 over k 1 minus q. Okay, and then if k is less than 2, that we will see is the case. Yeah, that this is solved by constant. Okay, so if we plug this into the expression for q, what we have is that if you look to this exponent, to the argument of this exponent, you just have, so you have, apart from the sign, you have h squared times v of q, and therefore this is h times 1 minus q to k minus 1 over k. So you see that the p of q and h for h going to minus infinity becomes a function of this scaling variable. Okay? And you see that this is exactly the scaling variable that I've shown you at the beginning for the scaling assumption for p. Okay, so for h that goes to infinity, this is a smooth function of q when q goes to 1. And instead, when h goes to minus infinity, this is a function of this scaling variable. Okay? So, so now I will write the scaling variables for p.
So you made this ansatz just to argue that it's a scaling function of this variable, but then you forget about this ansatz.
Yes, I mean, I just say that because actually what happens for h to minus infinity, I will not discuss this, but
It's different.
no, it's non-universal. Okay, let me go to that. So you have here q and h. So at plus infinity, you have a regular function that I will call p plus of h. Then for h negative, you have something that is, okay, so you have 1 minus q minus k minus 1 over 2. Okay, we have h 1 minus q. So this is for h 1 minus q. And so you see that you have two regimes, and they have different scaling variables. Okay, so this is really h, and this is this scaling variable. So what happens so you should have a matching regime when h is of the order of 1 minus square root of 1 minus q when q goes to 1. And this is, so we say that this is 1 minus q. These are general answers. Okay, so this is how we get this form. Okay, so we analyze what happens at h plus infinity and minus infinity we get two regimes, and then in order to match them, we need to have a matching regime inside. Now, when you look at the equations, you realize that this function is not universal, so it's really fixed by the boundary condition. But it turns out that when you take this form and you plug it inside the equation for p, then you have a closed equation for p0. This is universal. Okay, so when h is of this order, then you have a scaling equation for p0. Okay, and this is really universal. It doesn't depend on anything, on any boundary condition. Okay. And the scaling equation is the following.
And P plus, it's just Gaussian?
No, P plus, for h going to plus infinity, yes. But then when h goes to 0, it has a diverging behavior. So it goes like h to the minus gamma. And remember that this function is connected to the distribution of gaps. So this tells you that the divergence of this gives you that the distribution of gaps has a power of behavior with a clear exponent. Okay. Okay, so when you plug this, then you get an equation for p0. The equation for p0 is the following. So you have a over k 0. Now let me call again this t. Look, note that this is exactly the same scaling variables as in the equation for m. Okay, so you see that there is a structure that is appearing. So the equation for m enters into the scaling regime, and they have exactly the same scaling variables as they should in order to have an trivial behavior. So the equation is plus 1/2 t 0 t prime equal to 1/2 t 0 . Okay. Oops. Okay, now, in order to, so of course this is the scaling equation, but we need to match this scaling function with these two regimes, right? So the way in which h goes to infinity here, and the way in which, so the way in which this function behaves on the right should match the way in which this function behaves on the left, right? Because these two should match. Okay. So let's just work out the matching. So for h negative, so when we take this function, so this should match this, right? So let's assume that p minus of t. So now this t is that scaling variable. Sorry for the bad notation, but this variable here. So let's assume that this goes like t to the theta. So this is when t goes to 0 minus. Okay? So we want to see what happens to this function when it goes to h that is 0, because you see, so you have, okay, maybe I can write a kind of line here. So you have this is h. So in this region you have p0, here you have p minus, here you have p plus. So when p minus is pushed towards h equal to 0, you should recover exactly the same as p0 when it is pushed to t2 minus infinity, and vice versa in this regime. So let's assume that this behaves this way, and p0. So since you should have a matching, also p0 as a function of t should behave the same way, right? So when you plug the true expression of this t and this t, they are not the same, right? Because this t is h times 1 minus q to the power, and this one is this one. So when you plug this, then you just have that this exponent theta is, you get a relation for this exponent theta, which is 1 minus k plus a divided by k over 2 minus 1. So do you want me to do it? You have just to plug a, this t. So here you plug h 1 minus q to minus k minus 1 over k, and here you plug h 1 minus q to the minus 1 half. So you see that you have h to the theta and h to the theta that go away, and then you have a relation for theta that gives you this. Okay. Then you do exactly the same thing for this other two.
I sorry, I do not understand why the theta should be the same.
Because you have
H should be the same power.
Ah, okay.
You should have the same power of h, otherwise. Okay? So for h positive, then you have p0 of t, it goes like t to the minus gamma, when t diverges. Okay, so you are pushing this regime in this direction, and p plus of t, now this t is h. Okay? This should go exactly the same way. So a, so t to the minus gamma. Okay. And when you do this, you play exactly the same game, and then you get that gamma is equal to 2a divided by 2. Okay, it's just algebra.
Yeah.
Now this is interesting because, of course, this gives you how this function p0 should behave at the boundaries. Okay. So let me take back the equation for p0. So let me write here the boundary conditions. So yeah, that p0 of t when t goes to minus infinity. So where you are pushing on the left, this goes like t 1 minus k plus a divided by k over 2 minus 1. And p0 of t going to plus infinity should be like t to the minus 2a divided by k. Okay, so you have an equation. So let's start from the beginning. We fixed k. Then we had an equation for m that has a unique solution. So you plug this solution inside this equation, and here you have an equation that is a function of p0 and a, right? And this should satisfy these boundary conditions. Okay, so it turns out that if you fix k, there is just one a. There is a function of k that satisfies both boundary conditions. Okay? So you see that this is a kind of eigenvalue problem, right? Because you have this h is kind of, you see that this is an eigenvalue problem for p0. Okay? So up to now we have two exponents, k and a, that is a function of k. And now we need a third relation that fixes k. Okay? And the third relation, actually, so the third relation comes from, so what we did is that we used the flow equation for f and the flow equation for p. So there are a few equations remaining. And what you can do is that you can take the equation, this equation, so we had an equation that was giving us marginal stability. And then assuming that we had a continuous path for q of x, so we had an equation for x. So let me write this way. Okay. Now what you can show is that when you plug the scaling ansatz, this equation is dominated by the scaling regime. Okay. So what really, so everything, so this equation actually becomes this. So you see here that again you have the same combination of x divided by lambda, and this gives you k minus 1 over k, and this is equal to 1/2. And then here you have n second. That's it. So you see that this depends only on the scaling regime, so the regime for which h is of the order square root of 1 minus q. So it's the matching regime, this one. Okay. So this is the equation that fixes k. So the way in which we get these exponents is this exponent is the following. We first solve for m. And this is a function of k. Okay. Then we have an equation for p0. So we solve for p0 and a. There is a function of k. And then we use this equation to fix k. So this fix k. Okay? So if you compute it numerically, these equations can be solved numerically with arbitrary precision. So you get an expression for k, a number for k that is 1.41574. It's pretty non-rational number. Okay. Yes.
I mean, all this depends on the answers you made on F, right?
Yes.
The two
Yes.
two regimes for H infinity and minus infinity.
Yes, for P. Yes.
Yeah, or for F. You did it for F first, right?
Yeah. We have H. Yes, we have the two asymptotic behaviors and the
C1
matching regime
and
inside.
the other one with the H squared.
Yes.
And how general is this? I mean, this picture.
It's general in the sense that, so you see that this asymptotic behavior for F, it's driven by the fact that if you when you have f of q, let me compute f of qm h. This is the log of gamma 1 minus qm theta. So the fact that you have a matching regime comes from the fact that this function has a jump at 0. And that's how you get that the two asymptotic regimes should have a matching region. It's this discontinuity that drives everything. Okay.
I don't know if you.
So it's general in the sense that.
I mean, okay, I have to have a matching, but what is the ansatz in the two regions is.
It comes from here.
I mean, you can obtain it from there.
I can obtain what happens as shown here, right? So for h going to minus infinity plus infinity, you have the two behaviors.
Oh, okay. Okay.
And I shown that when q is less than qm, but still close to qm, you have exactly the same behavior. You have 0 on one side and minus h squared divided
Okay,
by
so-
lambda on the other side.
Okay. Yeah, I thought
But
it
it's
was,
driven by this.
I thought it was an ansatz. Okay.
No, no, no.
I
It's,
missed the.
you can check it that it's consistent with the boundary condition.
Uh-huh.
Correct. There is
Okay.
So for instance, global, more like you have this line in alpha in sigma negative,
yes.
and this Gemin line, and so you computed this close to this line,
Yes.
and so still cool fact that this k could be in principle function of sigma, but it is not.
No.
It is universal.
Yes.
Okay.
I can tell you more. So if you take our spheres, so so this is something maybe I can use this. So if you take our spheres, so let me take the phase diagram. So here you have 1 over the pressure as a function of the density of packing fraction. So you have a line, this is the liquid line, the positional state of the liquid. And then here at some point you have this clustering transition, where the Boltzmann mesh gets printed, and each cluster is a glass. And now here you can consider compressing glasses prepared with different, let's say, compression rates. So you have the equation of state of different glasses. So you have 1, 2, and in principle here you have different jamming points. So one could have that these critical exponents depend on the jamming density, but then not. And you see, I mean, so these equations depend on the density only through non-universal parts, so P minus, for example, or P plus. But the matching regime that is just needed to match the two is really universal. That's why they don't depend on the points of the phase. Okay. So, so there is a scaling relation between these exponents. That is, and now I have it for gamma, but it's beta before I say yeah. So you can compute from k you get a, right? Because we say that at step 2, having fixed k, you just have one solution for a, and it turns out that a with the numerical precision is 1 minus k over 2. This is what we can find at the numerical level. So it's not clear how to derive this relation from the scaling solution. Okay, so this is a scaling relation between the exponents, and we don't know how to derive it. But there is an argument that I will tell you in 5 minutes, from which you can get this relation. Okay. So before telling you the argument, let me just. So we discussed already the physical meaning of this exponent k. It's how Qm, the size of the innermost clusters, go to 1. Okay, how they go to 1. And now I would like just to discuss these two exponents. So this one that we call gamma, and this one that we call theta. Okay. So these exponents you can work out in details by. I mean, it's not extremely complicated, but so theta is the exponent of the forces. So if you look to the negative gaps, okay. So in the language of source spheres, so suppose that you take the. Okay, let me do this way. Suppose that you take the jamming transition line. Now you remove their constraint. You put a soft constraint, as we did it, right? So we allow the overlap between spheres, and then we go to this line from above. So we can look at the distribution of small h. So this will just give us the distribution of the overlaps. And of course, this is connected to the forces that are accepted by the particles, right, by the spheres. So it turns out that these forces, that are just the minus the gaps, behave like f to the theta, for f that is going to 0. Okay, so the small forces have a kind of pseudo gap. Okay, that is of this form. And so if we know k, we can get this k, this theta. Okay, so this is theta, and gamma that appears there. You can show that is the distribution of gaps. Okay, so we had, remember we had h mu, right? It's the same h here. So it was 1 over square root of n psi mu dot x minus sigma. So you can plot the histogram of this h when for the ones that are positive. Okay, so you are here at jamming. You have some of them that they are at 0 because these are kind of contacts, and some of them are positive. So the distribution of the positive ones goes like h to the minus gamma. Okay. So you can compute the h goes to 0. So you can compute this exponent. Okay. And the last thing is that what you can show is that here marginal stability, so the other relation that I told you is the one that gives you marginal stability, so it's this one. This tells you that packings are isostatic here. So remember that in the convex regime, this on this line, on the jamming line, packings or the solutions to the problem were isostatic. We said here, when you are in the non-convex regime, the solutions become isostatic at jamming. Okay. So this is really related to the fact that you have marginal stability. So it's the fact that you have a Fourier SB solution that gives you that on this line you have isostaticity. Okay. Now I would like to show this relation. If you plug the expression for A and K, this becomes this relation. And there is a simple argument for this. It's a very physical argument to have this. And I mean, let me just tell you what is the argument. So this is something that was done by Mathieu Liard. I'll give you the reference. So the reference is Liard. So it's a PRL. Okay. So this argument actually is very similar to an argument that was done by Anderson in the context of spin glasses. I will not do the argument for spin glasses. But let me tell you what his argument is. So consider a packing. Now we move from the perceptron to real sphere packings. So this is a jammed packing. Okay? And it's isostatic. Now, what I would like to do is to study the stability of this packing. Okay. So if, for example, I take two spheres that are in contact, so they are exerting a force between them, they apply exactly a dipolar force that is opposite to the force that they are exerting in order to open this contact. Okay? So if I do this, what you can do is that you can show that the pressure at which the packing is, that's the variation of the volume that you induce by opening this contact. So when you open this contact, you are just changing the total volume of the system because the system will tend to expand at the beginning. So this is given by S, where S is the amount, so the amount of which I'm separating the spheres. times the force that I'm applying, and I have a nonlinear correction that is due to the disorder here. There is a constant times n, where n is the total number of spheres, times s squared. Okay? So if you plot this function, this is a parabola, right? So it's something like that. Okay. Now, since I want to destabilize this packing, what I can do is that I can take the smallest force. Okay, if I take the smallest force, is where actually the two spheres are accepting the smallest force between them. So it's really the weakest contact. Okay, so let me take F, that for the moment is arbitrary, as F min, the minimal force. Okay. So what is the scaling of this with n, with the system size? So assume that the distribution of forces is F to the theta. Okay? As we have shown here. So if you assume this, then the minimal force is simple to derive because you have just 1 over n is just the integral of the P of F from 0 to F min. Right?
Mm-hmm.
And this gives you that F min goes like m, now I don't want to make mistakes, to minus 1 plus 2. Okay? Okay, so what happens? So you apply this force, so there is a gap S that is opening. So if you open a gap more than this value, F equal S star, F equal this S star, then of course you gain volume, right? Because the volume becomes, the delta V becomes negative. Okay? So this is the limit of stability. If I go beyond this point, if I open the two spheres beyond this point, then I am destabilizing the packing, and the packing is rearranging in a more compact configuration. Okay. But what happens? It turns out that, so when you are opening these two spheres, you are making the system from isostatic to hypostatic, right? Because you are removing a contact. So when the system is flowing and you are increasing S, it could be that at some point there is a new contact that is forming in the system. So the sphere, two spheres will touch, and there will restore isostaticity. And then there the flow blocks, right? Because if a system is isostatic, it's mechanically stable, it cannot flow. So what we want to do is to estimate what is the typical S at which a new contact is formed. How do we do? Well, we assume that this typical S, where the new contact is formed, is of the order of the minimal gap between the spheres, okay? Between spheres that are not in contact. So when they flow, it's very likely that the first contact that will be formed, the first new contact, is between two spheres that were very, very close. And so it will be of the order of the minimal gap between two spheres that are not in contact. So how does this behave with n? It's simple, because we assume that the P of H, again, is like here. So it's H to the minus gamma with another clear exponent. And H min, you do exactly the same thing. So from 0, this is 1 over n. And then this gives you that H min is of the order of n minus 1 or minus 1. Okay, so you have F min. So this F min gives you an S star. So what do I write? Okay, right here. So this S star, if you use this F min, in this equation is like n2 minus theta plus 2 divided by 1 plus theta. And so in order to have a stable packing, what you can do is, so the condition for stability is that this H min is less or equal, and this is marginal stability, to SF. Okay, so you have n minus 1 minus gamma, that should be greater or equal than n to
2 plus 3.
here, this one. Theta plus 2 divided by theta plus 1. So if you do that, what you get is gamma greater or equal than 1 over theta plus 2. Okay, so what happens is that if you take real packings, this bound is saturated. So you have an equal sign here. Okay. And that's what we get from the solution in the perceptron. Okay. So these exponents are really the same. So the exponents, numerically, the exponents of the perceptron and sphere packings are the same because the scaling equations that give you these exponents are exactly the same. So that is it, yes.
So I got the derivation from the first one, but in the first equation, do you have an argument why the nonlinear term should scale with n?
Yeah, it's due to the I mean, you can compute the variation in energy of the system. You can compute it. It's capable. I don't want to.
Instead, I lost when you write that 1 over n is equal to the integral of p.
Yeah.
You wrote it 2 times. Why is that?
Okay. So
You
this
wrote
p, let me consider p of f. What is this? This is the fraction of forces that are equal to f. So it's the total number of divided by n.
Okay.
So you have. So the minimum of 1 is when you integrate this from 0 to h min, and this is 1 over n, right? Is it clear? This?
No, that's what
So if I do this, this is the histogram of forces, right?
yes.
Because this is really the number of forces that are equal to f.
Yes.
And so I want this integral, I want this just as to be 1.
If I integrate all the
I should get n, right?
yes.
So this one is just, in this interval, there is just one force. Okay? That's why. Okay. Okay. So what we found is that
And this exponent k, a, they also appear
Yes.
in other models.
sorry?
They also appear in some other models because this guy probably wrote his work before you.
Yes. This is a paper of 2012.
Yes. So, do they arise in which other models they arise? As k, a exponents.
Well, R spheres. So they appeared in R spheres. So in packings of R spheres. Then the studies that they had a series of scaling relations between them. Then we computed in R spheres from the infinite dimensional solution. And then it was realized that they were the same in the perceptron. And now the question is, how big is the universality class? Because the perceptron is a model that is different. It's a constraint satisfaction problem. Microscopically, it's really different. Then, when you look at the scaling equation, closed-loop, they are the same as our spheres. And the question is, can we create new models where these exponents are different? How big is the universality class?
So numerically, okay, it's numerology, but this exponent k is very close to square root of 2.
It's not.
Okay.
But okay. What else to say?
0.1%.
Okay, then I wanted to, the plan for today was to start also the cavity method, but I will try to do it in the last lecture. So the plan for the next lecture will be to use the cavity method to rederive the replica symmetric solution. And this is interesting because, we have seen here that, there is a lot of interesting things when you have replica symmetric breaking. But even the replica symmetric solution within the cavity method is really powerful in applications. For example, if you do inference or things that, for example, Lenka and Florent, they've done a lot. So I wanted to redo it in this case. And actually, you can show that using the cavity method, you can rederive some properties of the replica solution. So the two solutions, the two methods are equivalent, but they are different. One has some properties, some nice things. The other one has some other nice things, and it's good to see both of them. So that's what I would like to do. Okay. Questions? Yes.
So when we were doing the scale, so you did the asymptotics in h to minus infinity and plus infinity.
Yes.
But h is a gap, right? So shouldn't you have kind of cut off
No.
before you go to infinity?
No. H is not the gap. So h is just a variable. Then when you compute the scaling form, so you have a p of q and h, right? And the positive part for h positive, this function is connected to the distribution of gaps. So where they are positive. For h negative instead, this function is connected to the distribution of forces. And the forces should be for h negative, because if you have spheres overlapping, then here h is negative. That's why the negative part in h gives you the distribution of forces.
Okay, but I don't understand how it could be, for example, more negative than the radius of the spheres, or.
No, okay. So of course it depends on the. I mean, you are really going close to Q0. Then of course what happens at h that are very negative, then you will see that. I mean, it's something that is not universal.
Right.
Okay, and anyway, so the real answer is that in our spheres, this h, so this distance is, so suppose that the diameter is 1, so this distance, so so each position of the sphere is like x0 plus some fluctuation is on order 1 over d. So this h is how much the spheres fluctuate on a range that is of the order 1 over d. So I mean, you can go to h minus infinity just because you have a prefactor. Okay, but it's technical. I really want to enter into it. Okay. Yes.
But for instance, also keep maybe even it would be more complicated, but you have this line, and so you describe us what's going on to the right when alpha is positive, and when alpha is negative, somehow we have small, epsilon from this line. But if, for instance, I exactly at alpha equal to 0, and so it's kind of, trick, I don't know.
Yeah, it's something that we never investigated up to the end, but the idea is that the scaling regime just shrink to 0 when you arrive to sigma that is 0.
Yeah, not alpha exactly, sigma. Yeah.
So you have a scaling regime, and this scaling regime you can show that is. So for example, the P of H. But this is we've never done this in detail. So yeah, the P of H, the P of H for H positive, when you are in the positive sigma part, you can show that it's kind of Gaussian. And then when you approach to sigma, or let's say the other way around. So in the other, for sigma negative, you have a divergence. And the range in which you have this divergence just shrink to 0 when you go to sigma that is equal to 0. That's how it should be. But we never check. We never check. Because, I mean, the point is that you see that it's very singular, because here you have the line that separates the replicas.
No, I understand, but maybe so because it's so special point, you still can expand and find, somehow, as you have this P0 function, which kind of allows you to match these two regions. So here you may also find.
I got the same observation by David Gibbs. He told me exactly, why don't you look to this kind of three critical points?
That's right, kind of three critical points.
And but it's still never done, because I think what happens is that you have to rescale everything in terms of this distance. Right. So there is this distance is going to 0. You have to introduce it.
Right. You have to do.
But it's not.
You have to walk again hard.
I mean, you can have a perturbative regime close to this line, but it's not clear if this perturbative regime. I think no, but we have to check that this perturbative regime close to this point extends up to the German point. But to be honest, I've never done the computation.